Clue what I'm talking about. So, and we don't get a lot of snow here, but I was at a workshop and somebody explained horizontal asymptotes this way, and I'm like, gosh, I wish I would have known that for the last 20 years. So when you go make a snowman, and let's say we only have enough snow in Alabama to make two spheres for the snowman, okay? We want the top to be smaller than the bottom. Do y'all agree with that? When we go to make a snowman, we want the top to be smaller than the bottom. So I want you to draw a snowman. We want the top to be smaller than the bottom. Why do we want the top to be smaller than the bottom when we make our snowman? Because if the top were bigger, it would just what? It would just crush it. It would just fall over. Okay? So this snowman represents the first rule of horizontal asymptotes. It says if the degree in the numerator in the top part of the snowman is smaller than the bottom, then there will always be a horizontal asymptote at y is equal to 0, which is the x-axis. So if you can make a snowman, there's going to be a horizontal asymptote. If the top is smaller than the bottom, then there will always be a horizontal asymptote at y is equal to 0. That's rule number 1 in snowman language. Rule number 2, if the degree in the numerator is larger than the degree in the denominator. Let's draw that snowman. Rule number 2, if the degree in the numerator is larger than the degree in the denominator, what's going to happen to that snowman? It's not going to be a snowman. It's going to crash to the ground. It's going to tip over. So if the degree in the top is larger than the degree in the bottom, will we have a snowman? No. And so that means we will not have a horizontal asymptote. If the degree in the top is larger than the degree in the bottom, we will not have a horizontal asymptote. No horizontal asymptote. Okay? Rule number 3 in snowman language says if the degree in the numerator is equal to the degree in the denominator. So let's make a snowman where the top snowball is the same size as the bottom snowball. Could that work? Could I make a snowman if both snowballs were pretty well equal? I could, okay? It really wouldn't look like a snowman because we know the one above, the snowball above always needs to be a little bit smaller, but it wouldn't crash because the top's not bigger than the bottom. So I will have a horizontal asymptote here because I can have a snowman under this situation. And you find the equation for that horizontal asymptote by doing y is equal to LC divided by LC. We've used the abbreviation LC before. What's LC stand for? Leading coefficient. Okay? Sometimes these rules are hard to memorize. So to me, the snowman example would help me. It would make this stick, kind of like snow sticks, and we don't get a lot of snow around here that sticks, so we really don't know about that. So first of all, the snowman that can't exist is when the top is bigger than the bottom. So anytime the highest exponent in the top is bigger than the highest exponent in the bottom, there's no horizontal asymptote there. If it's a perfect snowman where the top is smaller than the bottom, there'll always be a horizontal asymptote at y equals 0, which is the x-axis. If the top degree and the bottom degree are exactly the same, then you'll find your equation for your horizontal asymptote by doing y is equal to the leading coefficient in the top divided by the leading coefficient in the bottom. Okay? Questions? The next thing on your notes is slant asymptotes. We will come back to that. We will really want to deal with vertical asymptotes and horizontal asymptotes before we do slant asymptotes. So we're going to skip the slant asymptotes for right now, and we're going to move on to some examples. So they're asking us to find horizontal asymptotes in the first 4 examples. So using our snowball illustration, in example 1, what's the degree in the numerator? 1, what's the degree in the denominator? 2, can I make a snowman if the top degree is the top is smaller than the bottom? Yes, I can. And the horizontal asymptote will always be at y is equal to 0. You got to have the y because that tells you it's horizontal. If you had an x equals a number, that would be a vertical asymptote. Example 2, right below that, what's the degree in the top? Y'all looking at example 2? Example 2, it's below that. Degree in the top is 2, the degree in the bottom is 2. So this time the degrees are the same. So I am going to have a horizontal asymptote, but it's going to be at y equals leading coefficient divided by leading coefficient. If you've forgotten what a leading coefficient is, it's the coefficient of the variable with the highest exponent. Will 15/3 simplify? Yes, so I will have a horizontal asymptote at y is equal to 5. Close. Example 3, h of x is equal to 15x cubed divided by 3x squared plus 1. No horizontal asymptote, so I'm just going to write none. None because the top degree is 3 and the bottom degree is 2. That snowman would be crushed. It wouldn't work. If top is bigger than bottom, no horizontal asymptotes. Example 4, f of x is equal to negative 3x plus 7 divided by 5x minus 2. What's the degree in the top and the bottom? 1, so they're tied. I will have a horizontal asymptote, and it will be at y equals what? Negative 3/5. That's about negative 0.6. So I would have a horizontal dotted line down about negative 0.6 units, and it would just be dashed across my graph, and my graph would approach that horizontal asymptote. Okay, that's explaining your horizontal asymptotes. Where do vertical asymptotes come from? Excluded values from the denominator. Horizontal asymptotes come from your 3 rules. Yes?
Do you want us to keep it as a fraction form, or do we make it decimal?
You're graphing, so the question was, do you want to keep it as a fraction form? You write it however you can graph it. So to me, it would make more sense to change that last one to negative 0.6, okay? All right, in the rational function world, we do have 2 graphs that we consider common. These are common graphs, so we're going to memorize these common graphs, just like vertical snakes and horizontal snakes and shooting stars and V's and parabolas and all those graphs that we have studied along the way, conic sections. These are 2 rational functions, meaning x's are in the bottom of these graphs, that we're just going to memorize these. So you might want to write the word memorize. And when we memorize graphs, we can use transformations on them. Okay, we can move them left and right and up and down. It won't get as bad as doing any vertical stretching or shrinking and all that kind of stuff. But you do need to know what these 2 graphs look like. Okay? So, let's talk about vertical asymptotes. So, f of x equals 1 over x. Look in the denominator and see if there are any excluded values. Any excluded values for f of x equals 1 over x? We'll do the graph on the left first. X cannot be 0, so I'll have a vertical asymptote at x is equal to 0. Because x can't be 0, so the graph's going to approach the vertical line, x is equal to 0. Horizontal asymptotes, I'm going to have to use my snowman rules. So, what's the degree in the top if there's not an x? Most people don't know this, and I know that you... 0. So, if you don't have an x, you just have a constant term, then the top has a degree of 0, and the bottom has a degree of 1. So the top degree is smaller than the bottom, okay? And so that means there'll be a horizontal asymptote at y is equal to 0. If you don't have an x in the top or the bottom, the degree is 0. So the top is smaller than the bottom. Now, x equals 0 is which axis? X equals 0 is which axis? X or y, x equals 0, the y-axis. X equals 0 is the y-axis, and y equals 0 is the x-axis. Not many people commented there. Y'all get that? X equals 0, guys, is a vertical line. Y equals 0 is a horizontal line. I'm highlighting your axis because they won't ever dash the axis. Okay? If you have a horizontal asymptote or a vertical asymptote and they're on the y or the x-axis, they won't dash those. You just have to know that they're asymptotes. Okay? When we make a t-chart, and we're going to make a t-chart just for you to see what these two common graphs look like, and then you're just going to memorize them, just like the V and the shooting star and the vertical snake and all that. We're going to make a t-chart just for you to understand where the graph's coming from. So when you make a t-chart, you pick your x's around your vertical asymptote. When you make your t-chart, you pick your x's around your vertical asymptote. And what value can x not be? 0. So you're going to put 0 slap dab in the middle of your t-chart. You're going to pick a few x's to the left of 0. And you're going to pick a few x's to the right of 0. Because if 0 is where I have an excluded value, then I'll have two pieces to this graph. I'll have a left-hand piece and I will have a right-hand piece. If you have two vertical asymptotes, then your graph will have three pieces. If you have one vertical asymptote, then your graph will only have two pieces. So these are your notes. So I would take where you have x equals 0, and I would draw me an arrow to show I put the 0, because that is an excluded value, I put it in the middle of my t-chart. Then I'm going to plug these values in. When x is -3, y is what? -1/3. When x is -2, y is -1/2. When x is -1, y is -1. When x is 0, y is undefined. That's why there's an asymptote there. When x is 1, y is 1. When x is 2, y is 1/2. When x is 3, y is 1/3. Anybody got a question about my t-chart, where I'm getting those numbers? Your x's are going to come from left and right of your vertical asymptote values. Alright, so let's sketch this in. We know these are curves. All of these graphs are some type of curves. So let's sketch these in. These will be really, really small numbers, but we're just going to pretend that we are sketching them in. -3 1/3. That's a tiny bit. Or is it negative? Alright, forget I put that point there. -3, left 3, down 1/3. Left 3, down 1/2. Left 1, down 1. Okay? How many asymptotes are there in this graph? We highlighted them, yellow and green. 2. Both of those asymptotes are your graph, this little piece that we're graphing. Our graph is going to approach the green asymptote, and our graph is going to approach the yellow asymptote. And you see that we got a little curve going on between those 3 points? So what you're going to do is you're just going to sketch the rest of this in. I'm going to try to make my pen a little bit smaller. You're going to sketch the rest of this in. It's a curve. You're sketching it in, knowing that your graph is going to approach the yellow and the green asymptote. You're just going to sketch it in, just using those few points. We know these are all little curved pieces. We know they're going to approach our asymptotes. So I'm not going to make you find 100 x values. You only need to find about 3 on the left of the vertical asymptote and on the right of the vertical asymptote. You may have to find 4, but you probably can just do 3 if you understand the concept. On the right-hand side, we're going to do 1, 1, 2, 1/2, 3, 1/3. Again, that's going to produce a little curve. We can connect that curve, and then we know the ends of the graph are going to approach the green asymptote and the yellow asymptote. So we can just curve it in there. And then we're going to memorize this graph. So 1 over x has one piece in the first quadrant, and another piece of the graph is in the third quadrant, because this is going to be a common graph. So 1 over x, you have one piece of the graph in the first quadrant, you have another piece of the graph in the third quadrant, and you're going to memorize two ordered pairs. You're going to memorize 1, 1, and you're going to memorize, what's the other one going to be? -1, -1, and the rest of it's just going to be a sketch. Okay? It's just going to be a sketch. All right, let's look at 1 over x squared. Vertical asymptotes and 1 over x squared. Any excluded values in the denominator? 0. So I have a vertical asymptote at x equals 0. Tell me about the degree in the top compared to the degree in the bottom. Top is smaller than bottom, so I'll have a horizontal asymptote at y is equal to 0. So the asymptotes are going to be the same. I have a horizontal asymptote at the x-axis, and I have a vertical asymptote at the y-axis. If you want to highlight them, you can. You don't have to, but your axis won't be dashed. They'll be solid. All right, I'm going to make a quick t-chart here. Again, we're going to pick our x's around our vertical asymptote, so we know that x cannot be 0. So we're going to pick a few x's to the left of 0 and a few x's to the right-hand side of 0. So our graph is going to approach 0 from the left-hand side, and it's going to approach 0 from the right-hand side. That's why we have to pick the x's to the left of 0 and x's to the right of 0. So this time x is squared. So when you put in -1/3, what do you get? 1/9. Positive 1/9, by the way. -2. 1/4. -1. 1. You put in 0, you get an undefined value. That's why you have vertical asymptote there. When x is 1. 1. When x is 2. Positive 1/4. When x is 3. Positive 1. 9. Oh, all the y values here are positive. So I won't have any pieces of the graph below the x-axis. So this graph will look a little bit different. Its curved pieces will be the same, but they just won't be in the first and the third. So let's plot these real quick. And so we got a graph that we can memorize. -3 to the left 3 up a ninth. I know you can't graph up a ninth, but just pretend. -2 up a third, left 1 up 1. Again, this produces a nice little curve, and we know the curve is going to bend and approach both axes. We're really taking a lot of liberty here with just 3 points, but we know what the asymptotes do to our graph. It's like they're magnets, but the graph never touches the magnet. It's like the magnet just draws the graph closer and closer to the asymptote, but doesn't touch it. All right, 1, 1. 1, 1, 2, 1/3, 2, 1/9, and I know we're just guessing there. And then we're going to sketch those in. So if you have 1 over x squared, then you're going to have two pieces, and they're going to be in the first quadrant and the second quadrant. When you do your transformations, you're going to use the point 1, 1 and the point -1, 1. Those will be the only points that you use, and you'll just move the graph up, down, left, right, whatever's going on in the transformation. All right, so you will have to memorize that 1 over x has two pieces, one in the first quadrant, one in the third. 1 over x squared has two pieces. They're in the first quadrant and the second quadrant. All right, let's look at some of the transformations. Sketch using transformations. So if you're wondering if you're supposed to use transformations, guess what the directions will say? Use transformations. All right, so example 5 does not have an x squared in it. Example 5 does not have an x squared in it. It has 1 over x minus 2. So this is the graph that will have a piece in the top right and a piece in the bottom left because it doesn't have the x squared. The transformation, that's really x minus 2. The minus 2 is not on the outside. So who remembers if the 2 is being directly subtracted with the x, which way we move? We move to the right 2. Okay, you have a transformation rule sheet if you need to go find that. That was section 2.5. We're going to move to the right 2. If we move to the right 2, that's going to move your vertical asymptote. If you move to the right 2, that's going to move your vertical asymptote. It will not move your horizontal asymptote, but it will move your vertical asymptote. So what I'm going to do next is I'm going to sketch in, actually I'm going to use my highlighter. I'm going to have a vertical asymptote at x is equal to 2. I'm going to do that with a yellow line. My horizontal asymptote won't change. It won't change unless the graph is being moved up or down. So if the graph moves left or right, the vertical asymptote will move. And then from your new origin, we kind of have a new origin when we do these transformations. From your new origin, which is right here at the point 2, 0, you're going to go over 1 and up 1. That represents the point 1, 1. From your new origin, not this origin because the graph got transformed over. From this point, you're going to go over 1 and up 1. Put a point. Sketch in the right-hand side of the graph. And then from that new origin, you're going to go to the left 1 and down 1. Put a point in and sketch in the left-hand piece. So you won't be making t-charts with your transformations. You'll have to know what 1 over x looks like, and you'll have to know what 1 over x squared looks like, and then you'll just move the graph and just use those 2 points. Yes?
Can you explain how the graph again?
We're moving to the right 2 because it's x minus 2. When you have minus 2 to your x, that's a shift to the right. So the whole entire graph moves to the right 2. So once you go to the right 2, where the yellow and the green line intersect, from there you're going to go over 1 and up 1, to the right 1 and up 1, and then you're going to go left 1 and down 1, and those will be the only 2 exact points that you have, and you'll sketch the rest of it in.
Alright, thank you.
Alright, example 6 doesn't have an x squared in it, so it's the same graph, except it has a plus 1 on the outside. What's that plus 1 going to do? It's going to move it up 1. When you go up 1, that changes your horizontal asymptote. Okay, when you go up 1, that's going to change your horizontal asymptote. So I have a horizontal asymptote at x is equal to 1, but my vertical asymptote is still at x is equal to 0. It doesn't move because the graph just moves up. The graph just moves up. So where your vertical and your horizontal asymptote cross, that's kind of like your new origin. So you'll just go to that new origin, which is at the ordered pair 0, 1. And from there you'll go over 1 and up 1, right 1 and up 1. And then left 1 and down 1. Over 1 and up 1, left 1 and down 1. And then you'll sketch in the 2 pieces. Example 7 has 2 moves. What's the x plus 2 telling you to do? Left 2, and then the minus 2 on the outside is telling you to go down 2. Left 2 and down 2. So if we go left 2, that's going to move our vertical asymptote left 2. If we go down 2, that's going to move our horizontal asymptote down 2. So it's going to move the whole entire graph to the left 2 and down 2. So if you'll just move your asymptotes, then you'll have a new little origin where the vertical and the horizontal asymptotes cross. What's the ordered pair of that origin? Negative 2, negative 2. I know my asymptotes are kind of fat. I'm just trying to draw them so you can see them. They're fatter than they should be. So your new origin is at negative 2, negative 2. So from that new origin, you're going to go to the right 1 and up 1, and then to the left 1 and down 1, and you're just going to sketch in your graph. These are supposed to be curves. They kind of look like right angles. They're not supposed to be right angles. We'll kind of highlight them in there so they look like curves. Now, all three of those were 1 over x transformations. Example 8 has an x squared in it. So it's going to be that second common graph. Okay? What's the transformation in example 8? Left 1. What asymptote moves if we go to the left 1? The vertical one's going to move. If you go to the left 1, you're going to move the vertical asymptote. So we're going to go to the left 1. So our vertical asymptote will move to the left 1. Our horizontal asymptote does not move unless we go up or down. And then since this is an x squared graph, from the new origin, which is at -1, 0, we're going to go over to the right 1 and up 1, and we're going to go to the left 1 and also up 1, because on your x squared graphs, all of your points are going to be above the x axis, unless the graph is actually moved down, but the concept, and those points should be side by side, and they're not. Let me make that look a little bit better. And then you'll sketch in these two curves. And I kind of always think about the x squared as when a band director leads the band, you know, the x squared is more like what a band director would do. So the band director would lead like this. Actually, if it was in 4/4 time, it would be dun, 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 right? So the band director is the 1 over x squared. The 1 over x is really hard. Y'all try to do 1 over x. So 1 over x is where you have those two pieces that look like this. 1 over x squared is that. Questions about those two common graphs? You're going to want a common graph because you're going to have an idea of what it's going to look like. These are common. What we're fixing to get into next are not common. So on your common graphs, you just have to memorize what 1 over x looks like, do the transformations. You got to memorize what 1 over x squared is and use transformations there. All right. We'll talk about 9, but we're kind of running out of time. What are the transformations in number 9? To the right 3 and up 2. And then this graph is this one, right? Okay. So let's not do the whole graph there. We've got to move on and get to the other graphs. So the transformation on example 9 would be to the right 3 and up 2. That would move the vertical asymptote to the right 3 and the horizontal asymptote up 2. And then you would sketch in your y over 1 over x squared graph. All right, let's get to the big stuff. All right, here we go. 7 steps to graph the rational functions. Now, I've narrowed this down a little bit. Okay? I actually don't determine symmetry. I'm just going to be real honest with you here. I don't determine symmetry. I don't find the y-intercept. I don't find the x-intercepts. I start my process by finding the vertical asymptotes. So the first thing I do, I wrote these down so when you get to your book and they tell you to use these 7 steps, you can tell them that you know a little bit more than they do, and you're just going to start with finding the vertical asymptotes. Then you're going to find any horizontal asymptotes. Then you're going to find points between and beyond each and mark out x-intercept. You're just going to find points between and beyond each vertical asymptote. All right, and then number 4, you're going to graph the function. So I'm going to narrow it down to 4 steps for you. We can find symmetry, but I promise y'all can find vertical asymptotes and horizontal asymptotes really, really quick. Then you can make a t-chart and you can sketch the graph. We don't have to do all that stuff. All right, so we're going to narrow it down to 4 steps. Let's look at the first one. All right, example 10. This is not a common graph. Okay, who can tell me why it's not one of those 2 common graphs? Okay, it doesn't have a 1 in the numerator. It actually has a 3, and it also has an x. So example 10 and example 11, all the other examples, they're not common graphs. So you have to follow those 4 steps. Step number 1, find any vertical asymptotes. X is equal to 1. Use the snowman test to determine if there are any horizontal asymptotes. Yes. Where's the horizontal asymptote going to be at? How about y equals 0? Not y equals 0. Y equals... Say it louder. 3. Y'all get that? Okay, the degree in the top is 1 and the degree in the bottom is 1. So the degrees are tied. They're the same. When the degree is tied, it's leading coefficient divided by leading coefficient. So it'll be 3 divided by 1, which is 3. Does that make sense? All right, vertical asymptote at x equals 1, horizontal asymptote at y equals 3. Make a t-chart. Pick x's around your vertical asymptote. So what value can x not be? 1. So put 1 right in the middle. We know when x is 1, y is undefined. So we need to know a little bit about the piece to the left of 1. So pick 3 x's to the left of 1. 0, -1, and -2. Pick 3 x's to the right of 1. 2, 3, and 4. I could actually make you pick more, but if you understand what the asymptotes do to the graph, you can sketch the graph here. Now you're going to have to plug these values in. You can either use your calculator. This one's not too bad. So if x is -2, 3 times -2 is -6, and then I have to put a -2 in the bottom, that's going to give me a -3, right? -6 divided by -3 is a +2. And then some of y'all said this is just too much work. I'll just won't do this. Maybe she won't put any of these on the quiz. Wrong. X is -1, so I might have to write this down. X is -1, so that's going to give me a -3 in the top, a -2 in the bottom, so that's going to be +1.5. And I probably will use some decimals if it's probably easy for me to do in my head. When x is 0, you'll have a 0 in the top and a -1 in the bottom. 0 divided by -1 is 0. When x is 2, you'll have a 6 in the top and a 1 in the bottom. So y would be 6. When x is 3, you'll have a 9 in the top and a 2 in the bottom. So that gives you 4.5. When x is 4, you'll have 12 over what? 3, which simplifies to be 4. Any questions about how I did my t-chart? All right. Be careful if you're using your calculator. Really make sure you understand how to put all that in if you're going to put it all in your calculator. Y'all good with the t-chart? Alright, so I don't usually use graph paper here just because it's really hard for your asymptotes to show up. So I usually just sketch these on my notebook paper. The first thing that I'm going to do is I'm going to draw in my asymptotes. They are extremely important. Probably the most important part of the rational function graphs are the asymptotes. If you do not get the asymptotes right, probably nothing else will be right. Alright, so I have a vertical asymptote at x is equal to 1. I have a horizontal asymptote at y is equal to 3. I'm going to extend my vertical asymptote up a little bit. Anybody know how many pieces of this graph we're going to have? How many pieces does this graph have? 2. It will always have 2 if there is one vertical asymptote. There'll be a piece on the left and there'll be a piece on the right. If there's 2 vertical asymptotes, then there'll be 3 pieces. One on the left, one on the middle, and one on the right. Alright, -2, 2. Now, when you're doing these graphs that are not common, you go straight to the original origin, okay? You don't go up to the new origin unless you're doing a transformation. So you got to tell your brain, go to 0, 0, and then graph the first point. Left 2 and up 2. Next point, left 1 and up 1.5. Next point, 0, 0. So what those three little points are going to do is they're going to create a curve. You can see that's a curve there. And then you're going to take the liberty of drawing that curve in between those 3 points and making the curve approach your horizontal and your vertical asymptote. You change colors here. So we're really taking some liberty here. We just have those 3 points, but we'll draw in the curve between the 3 points, and then we'll make that piece bend towards the 2 asymptotes. Then we're going to do the same thing on the right-hand side of the graph. So the first point is 2, 6. 2, 6. 3, 4.5. 2, 3, 4.5. 4, 4. And then again that produces a little curve, and so you got your little curve, and then you'll just bend the graph up and you'll make your graph approach your 2 asymptotes. These problems do take a good amount of time. The transformation should not take a lot of time. You have 1, 2, 3, 4, 5, 6 homework problems tonight, and that's it. Okay? 6. Well, look at this one that we just did. Yeah. Okay, we got just enough time to get one more example in. Let's look at example 11. I'm going to erase 10s. Everybody got 10? All right. So we're going to narrow down our 4 steps. What's our first step going to be? First step, vertical asymptotes. Vertical asymptotes come from excluded values in the denominator. 1 and negative 1. 1 and negative 1. How did we know that? Well, the denominator will factor. So if you need to factor it, if you can't see the 1 and the negative 1 without factoring it, then you need to factor the denominator. So there are 2 vertical asymptotes, so this graph's going to have 3 pieces. All right, what about horizontal asymptotes? Y equals 0. Y equals 0 because the top degree is smaller than the bottom. So you always have a horizontal asymptote at y equals 0. All right, you're going to make your T-chart. This time we have 2 vertical asymptotes. So this is the part that people usually get confused about. Which value on my vertical asymptotes is the smallest? Negative 1. So you're going to pick 3 x's, and then you're going to put in your smallest vertical asymptote. Then you're going to pick 3 more x's. Then you're going to put in your largest vertical asymptote, and then you're going to pick 3 more x's. So you're going to have a left piece. That piece will be to the left of negative 1. You'll have a middle piece of your graph. That will be between negative 1 and positive 1. And then you'll have a right-hand piece. Those will be the numbers that are greater than 1. So what are the numbers to the left of negative 1 that we can choose? Negative 2, negative 3, negative 4. Then we're going to choose numbers between negative 1 and positive 1. And these are going to have to be decimals because there's not 3 whole numbers between negative 1 and positive 1. So it's going to be negative 0.5, 0, and positive 0.5. And then 3x's on the right-hand side of 1 would be 2, 3, and 4. And then we're going to painfully, this is the hardest part for me, this is the worst part. It's not hard, it's just time consuming. We're going to have to take all those x's and plug them into the equation. So let's do a few of them and then I'll tell you what I got for the rest of them. So let's do negative 4. 4 times negative 4 is negative 16. Negative 4 squared is 16. 16 minus 1 is 15. So when x is negative 4, y is negative 1 and 1, 15. If you want to do a decimal, you can, but we're going to estimate when we graph anyway. When x is negative 3, 4 times negative 3 is negative 12. Negative 3 squared is positive 9. 9 minus 1 is 8. That's going to be negative 1 and 4/8, which is negative 1 and a half. When x is negative 2, what's going to be in the top? Negative 8, and in the bottom you have negative 2 squared, which is 4. 4 minus 1 is 3. That's going to give you negative 2 and 2/3. Or you can use a decimal if you want to. When x is negative 1, y is undefined. And then this is where I would use my calculator, especially on the decimals. So y'all do 4 times negative 0.5, get that number, divide it by negative 0.5 squared minus 1. So 4 times negative 0.5 is negative 2 divided by negative 0.5 squared minus 1. Anybody get 2.7? That's the same thing as 2 2/3. I know I've got some fractions and decimals that won't matter when you sketch it out. 0. Can y'all do 0 in your head? When x goes in for 0 in the top and the bottom, y is 0. 0.5. 4 times 0.5 is 2. 2 divided by 0.5 squared minus 1 is negative 2.7. When x is 2, I can do these. It's going to be 8 over 2 squared is 4. 4 minus 1 is 3. That's 2 and 2/3. 1 is undefined. When x is 3, it's 12 over 8. That's 1 and 4/8, which is 1 and 1 half. When x is 4, that's 16 over 15. I see some symmetry in my t-chart. We skipped that step, but I can see it because my y's are popping up to be the same. 15. 1 and 1/15. Alright, we're almost out of time, so let's sketch this thing out. So we're going to draw our y-axis and our x-axis. We have 2 vertical asymptotes. One is at -1, one is at +1. And we have a horizontal asymptote at y equals 0, which is the x-axis. How many pieces are going to be on this graph? How many? 3. If you have 2 vertical asymptotes, there'll be 3 pieces. One piece will be to the left of the leftmost vertical asymptote. There'll be a piece in the middle, and there'll be a piece on the right-hand side. So -4, 1, 2, 3, 4, a little bit down. 1.5 is a little bit further. 2 2/3. Just kind of get your little curve there. Make your graph bend towards the asymptotes. In the middle, we have left a half up 2.7, 0, 0, right a half, down 2.7. So the middle kind of looks like a line, but it's really not. It'll be a little curve, kind of like a vertical snake. And then there's the right piece. 2 vertical asymptotes, you'll have 3 pieces to your graph.